And today we're going to talk about the Whitney Sum Formula. This will be a retake of a lecture that I previously recorded, but based on questions my students at the University of Oregon had. I'm adding a few details, trying to clean some things up. So right, let's start. So Whitney Sum Formula. Says that if I've got a direct sum of vector bundles, an internal direct sum, it suffices to consider, or external, then I can understand the Stiefel-Whitney classes as a sum of products of those of the constituent bundles. So let's do the first case. So theorem. So let E be rank n, F be rank m, then Wn plus m of the direct sum. In this case, there's only one term, and it's just the product of the Stiefel-Whitney classes, the top Stiefel-Whitney classes, the Euler classes of E and F. So the Euler class of the product is the product of the Euler classes, or really the Euler class of the direct sum, if you will, is the cup product of the Euler classes. So what's the idea? The idea is the Euler class is represented by zeros, and a zero of E plus F is both a zero of E and a zero of F. And I just said and that means intersection if we're thinking in terms of tome classes. So let's formalize that. So the proof is that by definition, Wn plus m of E plus F is, I'm going to assume I'm over a base manifold M, and then over M, I've got some section, and this is represented by, so it's represented by the tome cochain. It's a tome class of, I'm going to let sigma be a section. So let and then I'm going to look at the pre-image of the zero section. So this is my notation for zero section, just zero of the bundle E plus F. Okay, so zero E plus F, that's the zero section. Okay, and but as I said, the idea, and we'll apply that informal idea that zeros of the direct sum are intersections of zeros of E and zeros of F. So in fact, well, let's see. So sigma is really sigma E plus sigma F, two sections of a section of E and a section of F. This is immediate by definition. So what this is then is, sigma inverse of 0 E plus F is sigma E inverse of the zero section of E intersected with, and we're assuming some transversality here, sigma F inverse 0 sub F. But one of the main things we showed is you know, basically tau V intersect W is tau V cup tau W. And if I apply that here, what I get is that, so I would have an equality with tau of sigma E inverse of the zero section on E cup the preimage of the zero section on F, and that's just Wn E times Wn F. And that's what we wanted to show. So, so there that is. Let me zoom out a little bit so we can see more of the argument at one time. So it's really that these zero loci on M, again, for the direct sum, are just the intersection of zero loci of the individual bundles. And we prove that at the cohomology level, zero loci, intersection is cup product. Let me give a second proof. This was a proof using representatives down in M. I just want to do this proof in part to get used to arguing up in the total spaces of these bundles. So let me just indicate we're done here. But if we want to give a second proof, which I do, well, this Wn of E, we just argue that it's represented by, depends on where we're looking at it. All the following spaces are homotopy equivalent. So we just took a section of E that's transverse to the zero section and looked at the preimage of zero section, and and then the tome cochain of that is representative on M. The way to see that, the immediate definition we gave is just the zero section on E is the canonical representative, so then we pull it back to M. But if we're going to look on E plus F, then I claim the representative is the zero section of E plus F. I'm using the fact that the zero section is, yes, I was using it before as a map. By abuse, I'm now thinking of it as a rank zero bundle. And so then this sits inside E plus F as a subbundle. And the claim is that that subbundle also represents the Euler class. You can do this in a number of ways. E includes in E plus F as E plus 0, and then the preimage of 0 sub E plus F under that map will be the zero section of E. That's one way to prove it. I'll let you ponder whatever other ways, but just in different spaces, these cochains vary. They must. In particular, M, E, and E plus F all have different dimensions, so they better be represented by different objects because the codimensions must be the same. So then what we can say is that this cup product, so I'm going to work from the other side. Well, by definition, that's, again, the cohomology class represented by the zero section of E under what I just said, plus F, intersected cup with the tome class of E plus 0F. Similarly, but then again, we're going to use what we said before. The cup product corresponds to intersection if they're transverse. And in this case, they are. And this ends up being the zero section of E plus F, which is Wn plus M. So that's a second argument. Using cochain representatives not down on M, not on E or F, that it wouldn't make too much sense, but on E plus F. So M and E plus F are the two places where you can make your cochain argument. It's kind of more natural from a lot of people's perspective to argue on M, but we're going to find in the next case that arguing over the bundle of definition that we first define these representatives for Stiefel-Whitney classes is helpful. All right, so let's get to that next case. So so this takes care of all Euler classes, and so then the first non-Euler class So our next case is going to be the first non-Euler class. And what that is E and F are going to be rank 1. So first is by rank. And then if I look at W1 of the direct sum, that's not an Euler class. W2 would be the Euler class. And I'd have a formula for that. And Whitney sum says that should be the sum of the Stiefel-Whitney class, first Stiefel-Whitney classes of E and F individually. Okay, so let's recall our definitions. We're going to sort of give a pre-argument and then give a full argument. In the pre-argument, you can make a full argument if you're willing to expand our world of tome cochains a bit, which we're not going to do the technicalities for, just to say we're not wasting our time with this argument. It could actually be pushed through at this level if we want. So what are these levels? So let's recall that W1 of E plus F, what I have to do for rank 2 bundle is look at places where two sections are dependent. So that means I'm looking at E plus F plus E plus F. And we have this dependence variety, which is just a subspace where those two sections are linearly dependent. But the way to make a tome cochain with a smooth object is take the tautological bundle. So if I've got E plus F is fiber dimension 2, for two things to be linearly dependent in something two-dimensional, that must mean that they must lie on some line. So we take the space of lines in E plus F and 2 points on the line. So that means I've got an internal direct sum, because I'm taking the same line and I'm looking at the bundle over the Grassmannian as the space of lines. And then I'm taking 2 points on it, so that's 2 copies of the tautological bundle. And then if I take 2 points on a line, that'll automatically be dependent. So this is our dep2 hat, okay? And what I want to do first is just argue at the level of dep2, because then we're looking at subspaces of a bundle that's, I think, a little bit more hands-on. So at the level of dep2, what we're going to find, so the goal is to find a W such that the boundary of W is our dep2 union some submanifolds which represent W1E and W1F. So that's the goal. Well, let's give those somethings. Let's choose those representatives. I'm going to let the first thing be the zero section on E plus F plus E plus F. Okay. And B be E plus F plus E plus the zero section on F. Okay, and those are those somethings. I claim that that A represents W1E and B represents W1F. So in fact, these are just two codimension 1 subspaces. First thing to check is you've got the right codimension. Then second thing to check, okay, I can, I normally think of, again, the Stiefel-Whitney class of E, of the W1 of E as the zero section of E in E. But again, if I include E in this larger bundle, E plus F plus E plus F, as the first factor, plus the zero sections on everything else, then this A is going to be what pulls back or intersects, pulls back to the zero section on E itself as a bundle in E. So I could have also chosen the zero section on the third factor, but we'll see that these are this is a convenient choice. It'll give a slightly more standard names of things and coordinates. So again, what we want, so we want this W, it's going to be codimension 0. It's going to be a codimension 0 submanifold because it's going to be then a codimension, it's a 0 representing a 0 cochain whose coboundary is the sum of those 1 cochains. And what we're going to do is then apply then the coboundary of this tau W by what sometimes I call Stokes theorem, but anyways is just tau boundary of W. There's a minus sign in the oriented case, but of course we're working mod 2. This is then equal to tau of, if we get the right W, the union. But union in Thom cochains is sum, so that implies that 0 on cohomology, because coboundaries are 0, is going to be this tau dep2 plus tau A plus tau B. And these represent the 3 terms in the Whitney Sum formula. The first Stiefel-Whitney class of E plus F and E and F separately are these 3 terms. Here again, we're making an assumption that dep2 itself has a Thom cochain. That is true, although we haven't sort of done our technical work. So we're gonna follow this up with a second argument that that we have more of a technical basis for. But that's let's give the argument in that spirit. Okay, so what we're going to now do, and we're going to have to be very careful about this, is that we're going to argue in local coordinates. So we're going to try to define this W in local coordinates, and then we'll have to check that regardless of how those local coordinates work out, in any change of coordinates, the definition of W is consistent across those changes. So let's say, let's pick a basis locally. So in some coordinate patch, let call x the spanning vector for E, and y the basis vector for F. And then I can just name a point in this direct sum in coordinates. So then if I've got something in E plus F plus E plus F, then I can just think of that as some A times X, B, Y, another C, X, and dy. So locally, you give me 4 numbers, I've got an element of the fiber. So the other coordinate would need to be the base in the manifold, but we're going to ignore those. So these will sort of all happen over all base points similarly. So in these coordinates, then our submanifold A, which represents the Stiefel-Whitney class, first Stiefel-Whitney class of E, is going to be described by the subspace where A equals 0. So that's a description in coordinates, but it's actually independent of choice of coordinates. If I replace x by x sub x prime, 0 times x is equal to 0 times x prime. The 0 section is something that just exists regardless of basis. And its description in any coordinate system is just A equals 0, okay? And similarly, B is described in these coordinates by D equals 0. And then the fun is, we get to remember our elementary linear algebra, that dep2, well, let's draw the picture first. I'm going to think of E plus F as it's locally in R2. And it, in some sense it is, it's just can kind of twist around, but still even though it twists, I've got these sort of systems of axes, and that's the whole point of the Whitney Sum formula, is that I have a bundle that comes with this decomposition, and this decomposition, even though the bundle is twisting around, this decomposition twists with it. And so if I have my 2 different sections, A, B, and C, D, my 2 different points in the fiber, they're linearly dependent. They sit on a line. That'll come in the, play a much bigger role in the second argument we give. Well, that just means that AD equals BC, right? Elementary linear algebra. Let's go ahead and do the check that this is coordinate free, or coordinate independent, not coordinate free. I'm coordinate full, but coordinate independence. Let's suppose we replace x by, say, 2x. I could be fancy and say any scalar multiple. That then means that A is going to become A over 2 as a coordinate. That's my new coordinate. My A prime is A over 2. And C becomes the coordinate C prime, which is C over 2. And because AD equals BC, since I knew that, then under this change of coordinates, I see that A prime D equals BC prime, because both sides are over 2. So similar check on the, if I replace y by some scalar multiple. So this, even though I've used an equation in coordinates, is coordinate independent. And that's our representative of dep2, because that's how we say linearly dependent, because we took linear algebra once upon a time. So our W is going to interpolate between these. our W is going to be the collection where AD equals S times BC, where S is in the unit interval. Okay. So as we just checked for our dep2, for each S, we have that this equation will be coordinate independent. And so this collection over all S is coordinate independent. So W is coordinate independent. Check. So even though I've got that equation in coordinates, I change my bases. This set of points, this set of A, B, C, and D, so that doesn't change. So that means, and then we check that when S equals 1, we have the equation for dep2 implies we have dep2. When S equals 0, we have, well, AD equals 0. It means that either A equals 0 or D equals 0. And those are our equations for the our A and B. And so, yeah, this is the W we want. So W defines a subspace of E plus F plus E plus F, which cobounds the representing objects for A, B, and dep2, so W1E, W1F, and W1E plus F. And that would give the argument, once you also argued, I mean, just to have any co-bounding subspace, of course, isn't good enough if it's like a piano curve or something. We need smoothness, etc. Smoothness is problematic here. In fact, we'll come back to that. The fact is that this is quote unquote smooth enough. It's smooth away from some singularity. Let me make a little remark. So this would be a full argument once we know that that we can use, in particular, use dep2, not dep2 hat, as we will recall in a moment. And similarly for W. Let me make a little remark. Oops. That we can more clearly see the singularity of dep2. It's sort of the cone on the following smooth object. If we take, again, AD equals BC and intersect it with S3, right? So if AD equals BC, then I've also got some other number I can associate. Just take the 4 tuple and maybe look at its distance from the origin. And these are all diffeomorphic for any positive values of the distance from the origin. But then these all sort of collapse on the origin. And yeah, and I think sort of analytically, algebro-geometrically, I think that dep2 is really the cone on this object. So the singularity around 0 is a singularity of this of a cone on something two-dimensional, and that's why can actually then be used as a tome cochain. Good. But now let's breathe. We've made this argument at the level of depth 2. Again, if we believe in tome cochains with some kind of singularities and we look a little closer at the singularity, we would have a full argument now for the Stiefel-Whitney classes, the first Stiefel-Whitney class on direct sum, the Whitney Sum Formula, the first non-Euler class case. But now let's make our way to a more full argument. Okay, so let's argue about depth 2 hat. So we need to So this is again where we not only have dependent sections, so depth 2 hat, but we remember these lines. So I've got an internal direct sum and if I take a point on each, 2 points on that same line, I've got 2 points in E plus F. So again, this is an internal direct sum. Okay. And we're gonna, and let's remember that this really sits over GR1, which is, I could also call it P on E plus F, the space of lines in E plus F. There's no good comparison between these two bundles, but everybody then sits over M. Might as well remember that. Okay. What I'm going to do is really think of this as inside something that I'm going to call gamma 1 cross gamma 1 of E plus F, which is not quite an external direct sum, because what I want is that would just be 2 lines in E and F. You know, external would be 2 lines in E and F over M cross M. So really what I want is 2 lines in E and F in the same fiber. So let me name this, let me define this space just briefly by saying it's 2 lines in the same fiber of E plus F. Okay, so that sits naturally over some place that I'll call, some space that I'll call, that's a total space of, you know, and sort of, let me say, and a point on each for the tautological bundle. And here is just going to be the space of 2 lines alone. And I'm just going to call that GR1 cross GR1. Oops. Okay. So I've got a line and 2 points versus 2 lines in the same fiber. And there's a diagonal map here that says I can make a line from 2 lines, namely I'm going to say the same line twice. So this is a little commutative square, all of bundles over M. So this bundle also lives over M, and this also commutes. And this, this gamma 1 cross gamma 1, I can just remember those 2 points, and that sits over E plus F. So I really just want this first little triangle here, I'll go ahead and redraw the arrows in purple. I'm just saying that our original tome cochain representative, I can sit it inside some other submanifold. And the point is, and that's going to sit nicely over E plus F, and that's where the cochains on that bundle is where this argument is happening. And this other space is going to allow me to interpolate between my gamma 1 direct sum gamma 1 and something that's going to represent the other side of the Whitney sum formula. Okay, so again, so right, so dep2 hat represents W1 E plus F, i.e. the tome cochain of dep2 hat, which is now a smooth object. That's now something that our theory that we've defined so far covers. That tome cochain represents, coincides in cohomology. It's by definition that W1. And what I want to do is find that, what we're going to find, first let's find an A, which represents, and this will be in this other bundle, this gamma 1 cross gamma 1. Find inside there, and A, which represents W1 of E, a B representing W1 of F, and then a W such that the boundary of W is A union B union my dep2 hat. And as before, the argument, the Stokes theorem kind of argument will then say that the co-boundary of tau W is going to witness this equality of Stiefel-Whitney classes, W1E plus W1F plus W1E plus F. Okay, so the A and B are the easier parts, so let's talk about those first. Let's draw a little picture again. I've got E, F, language that I'll at least use in speaking informally, if not more formally. I'm going to call 0E plus F a vertical line because we're looking at spaces of two lines. So instead of the mouthful 0E plus F, let's just call those vertical lines because, well, it would be running up. It's that sort of fiber F. And E plus 0F is a horizontal line. And then what A is going to be is, so again, we've got collections L1, L2 in gamma 1 cross gamma 1, or I can say as subspaces of E plus F, such that I'll just write it as L1 is vertical. So L1 is this 0E plus F. And B is going to be similarly defined, but it's going to be L2 horizontal. And by the way, in this language, dep2 hat with, sorry, L1, and a point on each. And dep2 hat is going to be they're equal, right? So it's a line, but then, and a point on each. But a point on each, in this case, means 2 points on the same line. So that's our setup. What I want to do is, instead of arguing, I'm getting tired of saying point on each. These are going to come as bundles. So what I'm going to do is argue down in the, not gamma 1 cross gamma 1, but GR1 cross GR1, so to speak. So looking at, so let's consider, we're going to argue at the level, consider first GR1 cross GR1 E plus F. It's a bundle over M, so whose fiber over some fixed point M is going to be a torus. So that's nice. I like tori. It's one of the first spaces that we study in algebraic topology. So we have GR1 equals P1 equals S1, right? And here in this, I've got my vertical versus horizontal. In P1, it works like that. I mean, P1 is double covered. So instead of being at sort of 90 degrees, these are 180 from each other because, yeah. So in that case, the torus, S1 cross S1, if I take the vertical cross vertical line cross S1, I've got that. But then if I take the horizontal, or I guess that's vertical cross S1. Well, anyways, this is, I guess I should have called this S1 cross vertical, sorry. Just in our usual X before Y, meaning a Cartesian product. So let me correct that. I just change that. And this is horizontal, means that my second line is my, right, L2 is horizontal. I should draw this picture. Let me redraw this picture. Sorry. Let's see. So my my first point vertical means that I want this to be the subspace of vertical cross S1. This is a subspace of S1 cross horizontal. Or, instead of vertical cross S1, let me even say this slightly differently. This means I've got my first line is vertical and my second line is anything. Here, my first line is anything, my second line is horizontal. And then here is where L1 equals L2. So these are the things we're trying to co-bound. They're images in the Grassmannian. We're just going to take full fibers over these. And so the W is going to be the union of two triangles fiber-wise. So define W. to be, and let's call it W sub base, because it's not our W, it's down in GR1 cross GR1, to be the L1 cross L2 in GR1 cross GR1, such that the slope of L1 has the same sign as that of L2. And the slope of L2 is less than or equal to the slope of L1. So we, again, would have to be very careful here if we're trying to do this in coordinates. Really, I'm using some kind of map from the space of pairs of lines to, again, it would be a projective space. I might need to blow things up in order to do that. I would be blowing things up away from the points in question. So I'll just appeal to coordinates again, choose X and Y for basis vectors for E and F. We get numbers for slopes. Those numbers change a lot if I just choose a different vector, basis vector for X. The slope of L1 could be multiplied by 2. But if that happens, so does the slope of L2, and the sign is going to be the same. Maybe here what I want to say is absolute value of the slope of L2 is less than absolute value of the slope of L1. Both of their slopes can change, and then that inequality on absolute values will be preserved. So W is something that we can define coordinate free, even though it's not coordinate free, but it is independent of choice of coordinates if we want to go that route. So then the claim is, so let me just make the final claims and then give some technical notes. Because this is basically what I want to say is defining that. Then define, so the claim is that this W base is well defined in each fiber. I argued that verbally, but you can think about that more thoroughly if you'd like. So defines a W base globally, then you define W to be the total space of the restriction of this bundle, gamma 1 cross gamma 1 E plus F, to or over this W base. And then the final claim is that the boundary of W is A union B union dep2 hat. And that will give the argument. So I'm a little bit brief in these final words, but it really is sort of falls from this definition of this W. A warning, not really even a warning, just a note that there's a bit more technical work that we're going to have to go back in principle and address, because this W base, and therefore this W, isn't a manifold with boundary, which is what we've talked about for cochains. It's a manifold with corners. It's a union of two triangles whose boundary is 3 circles, right? I hadn't really thought of that subspace of the torus before. There's 4 of those, by the way. And you can see from the definition here, I could have also chosen them to have opposite slopes, opposite signs sloped, or I could have had the inequality go the other way. So there's these, the torus can be split into 8 triangles. That's the sort of star subdivision, the 2 diagonals and the horizontal and vertical. But if I take these pairs of 2 triangles, that's this this W base fiber-wise. And well, triangles are not manifolds with boundaries, but they are manifolds with corners. So go back, strike out, consider some W mapping to M, and think about the tome cochain there. W shouldn't just be a manifold with boundary. We should allow it to be a manifold with corners. So far, the main, we've done a couple technical things. Again, the cup product coincides with intersection. Didn't really care as long as we could, pull back things and get 0 manifolds. And the Stokes theorem, or in other words, and that's the last thing we apply, so that the co-boundary of the tome cochain of this W is giving the equality in the Whitney Sum formula. You then look at the preimage of something, and it's a 1 manifold. Now we would have to say 1 manifold with corners. But 1 manifold with corners are the same as 1 manifold with boundary. So our argument works, and W's like this, which have corners, are perfectly fine. So that is a fairly complete argument for the first case of the Whitney Sum formula. And I will stop there.